Uh, okay, so I can share my screen. Okay, so I hope the screen is visible to you. So yesterday we left off with MIMO antenna, and today we are going to start with the same. But today I have changed the shape a little bit. So let me reset this to previous design. So we have this base design antenna in which we have a simple microstrip patch antenna, and we designed this antenna to operate around 2.4 gigahertz. The exact frequency is 2.34 gigahertz. So we can slightly tune this frequency by controlling the length. So we want it to operate at 2.4 gigahertz, so we need to reduce the length of this patch antenna. So let me try with 28 mm. So uh, it is about this parametric sweep, and what we can do instead of deleting the parametric sweep, we just disable this from this checkbox, and now we are able to see that we have this marker, and now the antenna is resonating at 2.425. So if you want an exact results, you can slightly vary this, and let's say 28.5. So this optimization of the dimensions is all based on observation and trials. So it's slightly different. Okay, so that will cover this one. Now we just start the simulation, and now I am sure that we will be getting around 2.4. So copy this design and paste it here. So this has made a copy of this design. Now we can name it to MIMO. E. You can rename it by whatever name you want. And yesterday we made a design in which we made a mirror copy of this antenna. But today we are not going to make a mirror, but today we are going to make it side by side placement. Okay. So, if we see the result of this antenna, it is around 2.4 gigahertz. So we will consider this update. So now this exact same dimensions are here. Now in order to design MIMO antenna, first we need to change the size of this ground plane. So double click here, and what we want to place another antenna at the besides this. So let us increase the size in x direction. W extend, and I'm taking it as 100 millimeter, and click OK. So now our ground has extended. Similarly, we can apply this here. Yes. Okay. Now we copy this patch antenna and paste it. This is made a duplicate copy, or we can select this patch antenna and click here, that is move duplicate along a line. Then we select this line. In x-axis we are wearing, and we will not attach it to the original object, and click OK. Now when we see this operation here, we double click here and check its property. So now I am giving it a variable L move, and I am setting this variable to 75 mm. We can set it to 100 mm because we have extended the length by 100 mm. But currently I am selecting only 75 mm. Now we have duplicated the antenna, and it has the exact same dimension. Now this this port we have to make a duplicate also. So we select this again by the same method. Now go to duplicate line and set it to L move. So it will remain fixed relatively. Now you see, now the wave port has two components. Okay, and that means there are two wave ports. When we check it, the project direct project explorer, here we can see the excitations. It has two excitations, 1 and 2. But what happens when we duplicated it? So the port 1 has a well-defined integration line, but port 2, this port 2 has invalid integration line, because you see this arrow here, it is starting from the center of the wave port, and its end point was here. So this is directed here along this direction. Go to front. So the direction, you can see the direction of this port. So this is the integration line. It is extending beyond this wave port. That is why it is invalid. Now let's select this one. Let's delete it. So now we will select this port, and this we define this invalid line, and go to the, so now we have defined this node. Now if we see, this is well defined, and now let us go to simulation and analyze this. We don't have to make any other adjustment for this one, but just we will be getting some extra results. So this was our main design. Here we have the results, S11. This is S11, and you can see there are there only one port was there, so only one S1 parameter is there. Now we have two ports, so we will be having four S parameters. So here, now we have four parameters, so we select these two, and S11 is already there, so S21 we add this trace in our current plot. So you can see that we have less 30 dB of isolation between these two ports. And why we are getting a variation here? At here we are getting a frequency 2.35 gigahertz, whereas in our original design we were having In original design, we are having this at 2.4 to 2.39 gigahertz. So that difference is coming because if we go to results and check the simulation data, here we go for the profile and convergence. So here you can see that the maximum deviation in this, it is 0.09. Okay, uh, the delta maximum is 0.09, whereas it should have been less than 0.021, and practically it should be below that. Otherwise, our antenna is not properly converged. So the design was not converged, but we set the number of passes to 6. That is why it stopped here. So we have less number of meshes. That is why our results are not that reliable. Now we go to the MIMO antenna and select this one. Click on the top. Now you can see we are able to see this frequency, high amplitude electric field lines. And if I click here, go to the field overlays. In field overlay, let us click on this and right click, modify the plot. See the magnitude of electric field and click done. So we can see these waveport is exciting the field. Wave this waveport is exciting the field, and that field is being traversed along these lines. So when we right click here and start animating this, uh, 350. So we are making a variable of phase starting from 0 to 360 degree, and 35 steps are there. That means we are having a 10-degree steps. Now click animate. So from this distribution, what we can observe that in this part there is no uh, uh, signal transmission. So both of these antennas are isolated perfectly, and that is also concluded from here that the isolation is better than 30 dB here. Now, in our practical applications, when we are given some problem, we will not have this much task space. So for that, what we need to do, we need to optimize the antenna dimensions. We right click here and change the close visibility. So practically, we cannot have this much is for over 2.4 gigahertz antenna. We will be given size constraint. So we have to minimize the size of this by using any method. Then, in order to realize the MIMO antenna, uh, our customer will ask us to utilize this space as well, or he will say that do not place your antennas, or in whichever company you are working, you will need to place these two antennas very close. So let us try to place them closely. So we made this by moving. So I'm moving it, L move, I'm resetting it to 50. Now both the antennas are very close. Now there might be some problem with this. Let me see. If we check the port 2, because we have changed the position of this sheet, so it has moved. So no need to worry about that. Otherwise, there might have been an error regarding the placement of this wave port. Okay. So this line is integration line is there, so there is no need to worry. Now we have already disabled this, so we can uh, click on the analyze all button. Okay, so now we can see that the resonant frequency, the matching frequency is there, and it is the same, but the isolation and the return loss have been degraded. So why this is happening? Because we have placed our antenna too close. Okay. What happens if instead of 50, I try this with 40 mm? If 40 is too close, let us try to place it at 45, and let us check what happens. Okay. Let us take a 5-minute pause. Okay, so let's see what are the results. Okay, now we are having the results like this. Let us go to place the X marker and see what. So what happened just now, I will explain that later. So, we are having a return loss of minus 30 dB. That means all the power that is being transmitted from port 1, that is not returning to the same port. But that power, part of that power is being returned in port 2. That means if we are transmitting from this port, a part of that power is being transferred to this port. And the amount is approximately minus 12 dB. Minus 12 dB is approximately 15% or 8% maybe. 8% of the power is being transferred to this layer. So if we want to visualize this, right click here and animate the screen. So you can see at this point we are we can see some slightly coupling is there. So these antennas are coupled here. If we had placed this in other direction, then we might have got a higher coupling. Let me try this that one also. Uh, I am renaming it to MIMO E1. We will come back at this point. Then I'm creating another copy of this batch, and I'm giving it MIMO underscore TP. So just remove this. Now I will extend in y direction. I'll extend and let us set it to 100 mm first. Then I will set it to, I will increase the length of substrate also. Yes. So now we have a larger ground plane and substrate. Now create a copy with mirror. Select this and click here. Now select this mirror, and the base position refers to the point where we are placing the mirror, and the normal position refers to the direction of the mirror. So if you see the direction here, that is 0, 1, 0. So this is the normal position of the mirror. That means our mirror is parallel to x and z plane, and its normal direction is y plane. And we are placing this mirror in 0 degree x-axis, the center of the mirror, and we are placing in the y direction uh, LG plus LX divided by 2. So whenever you are using the variables, you have to calculate these dimensions. So instead of LX, I should be using LEX. And now click OK. This is for patch. Now let me create this wave port again, and I'm also placing this wave port with the mirror, and set this to 0 LG plus LEX divided by 2 and 0. Click OK. Now we are able to see this, and now check out this excitation. Right now this does not have any integration line. This one has a well-defined integration line. So let us go to the page so we can see this page. Select this page and place an integration line here. So now we have defined the integration line. And there is an error, boundary and excitation. Output must have okay. So the error is go to isometric view and fit all the elements. Now click on this region, so you can see that the region is starting in the from 0 in y direction, but it is extending well beyond. So that is why. So we click here, remove the padding in the y direction to 0, and click OK. Now it is okay. So now we can analyze our antenna. Okay, so right now you must be observing that my simulation is very fast. There are several reasons for that. First of all, this system specifications are there. We need to have sufficient RAM. But the major reason for this is in the setup, we have selected only 6 passes. Normally, we take it to 15 passes. And also, we have this maximum delta set to 0.02. Uh, when you are going for fabrication, you can start analyzing with 0.02, but when you are going for fabrication, you set it this setting to like this. Maximum number of passes 15, and the maximum delta variation, it should be 0.002 instead of 0.0. Okay, so right now I am not changing this. So that will increase the that will increase your accuracy of simulation. So now again we are able to see the variations here, and if I click here, go to S parameters, add S to 1, So this is S21. Now click S22, add the parameter. So there is a difference between S21. So if I had the accuracy set to higher number of passes and good accuracy, then my simulation would have taken much more time. And due to symmetry of the structure, I should have gotten this exact same. So that is the reason we are getting. But for demonstration purpose, I am only utilizing the lower end. Okay. Otherwise, for this structure, I would have to wait for 10 minutes at least for getting accurate results. Now, once we have done this, now what we need to do, we need to change the length. I'll extend, we set it to 45 again. And if we see now, 45 is more. We can set it to 35. Now let us check what happens. Okay. So from this field, we are able to see that it is interacting, and we have this S21, and when we are simulating it with better accuracy, then it might reach up to 15 or 10 dB. So that is possible. If we go to results, check the simulation, and for the convergence, the delta is 0.07. So that is very high. Okay. Now, if we see the electric field here, is right click here, go to modify report, magnitude electric field, apply, and click here to check it. Go to animation to set and check. So here both the radiating edges are nearby, so we have more coupling here. So that is also increasing this. Now we have seen same polarization in both the cases. The antenna is radiating same polarization. This one is radiating uh, positive uh, in this one is radiating in y direction. This one is also radiating in y direction. In this, we can see this one is radiating in negative y direction. This one is radiating in positive y direction. Okay. Now, these two uh, in these two, what we are doing, we are simply moving the position of our antennas. So that is known as spatial diversity. Spatial diversity, that means we are changing the position of antenna. We are keeping them far apart so that they do not couple with each other. So for this, we need at least lambda by 2 times the distance. So how do we calculate lambda? Lambda is basically the speed of light upon wavelength. So there is a direct formula 300 divided by frequency in gigahertz, and that is our lambda, and uh, lambda by 2. We should be having a minimum separation of 62.5 mm between these two elements. So that will occupy a very huge space. So now what we can do, we need to apply some characteristics that will we can apply some techniques to reduce this spacing, and we will check that out in a short period. So before that, I want to show you another variation that we can apply, that is uh, for polarization diversity. So again, copy this and paste original design, paste it, and we give it a MIMO T3. Now, if you this antenna is radiating in positive y direction, what happens if we rotate this antenna in by 90 degree? If we rotate this antenna with respect to z axis in 90 degree, then it will be rotated like this, and then polarization of the antenna will change. So here what we do, rename this MIMO, and so now in our third design, what we are going to do, we are going to extend this. Now we are going to increase the length of every parameter. In every means the width and length both we are going to vary. So let same thing we will be doing with substrate. Okay. Now our substrate is also extended. Now what we are going to do, we are going to make a copy of this one. So instead of creating copy from here, I'm creating a copy set by Control C and Control V, so that this is not linked with there. So when you are making this from here, when you are creating a copy from here, then all the parameters will follow in the new design. Whereas when you are simply controls copy and paste from Control C and Control V, it has created another object with the same operations, but both of these objects are not linked. So I'm creating it like this, and now I'm giving it a rotation in along z axis and 90 degree. Click OK. So what we can see, in z axis it has taken a 90-degree rotation. Now I need this antenna to be placed at this position. So for that, the coordinates of this ground, it is starting from minus WG, extending up to WG plus WEX. Okay. So from this point to this, it is WG, and this edge is at 0. So we WG by 2 minus WG by 2 placement displacement we are not considering. So now I will be applying a rotation here like this. This is a displacement. Now I click here and make it variable. So I'm going WG by 2 plus WEX. So hopefully this will move my antenna to this edge. Now I have to move it here also. So here I will be setting it to in Y direction. I am giving a displacement of WG by 2. So now the antenna is rotated. Now I need to select create a sheet and apply this here. So instead of creating a new, I am creating a copy of this rectangle. Then again apply the same movements. Sorry. First I need to apply the rotation. Then I need to apply the movement. So I'm a little bit lazy, so I'm just selecting from here and copy paste. Okay. So now if we see the isometric view, you can see that this is our patch 1 and it is excited by this port, and this is my second page and it is excited by this port. So is there any excitation associated with this? Yes. But select this one and check that the integration line is undefined, because originally the copy of this was created at this point. Now we have moved this so that the integration line is not moving along with this. So uh, let us do this and go to left, right, right, and select this, hit the selected button, and now I will change the integration line. Now it will work. Hopefully it will work now. Okay. Now there there is an error, that is the error is port to a wave must have solid inside. Okay, so the same problem is there. Again, go to this region and fit all. Then we are able to see that in y direction the boundary of this region is touching this surface, whereas
Sir,
uh,
screen
this
is not visible. Can you please share the screen, sir?
is it visible now?
Yes, sir. Now the screen is visible.
Okay, so how many steps I have skipped here?
Sir, 1 to 2 steps.
Okay, so uh,
Last 5 minutes, the screen is not visible actually.
okay, from last 5 minutes. So what we did in this test 3, we are trying to incorporate the polarization diversity in MIMO. So first we started with our ground plane. In ground plane, we gave an extension in width as well as length. Okay, so WAX and LAX, these are the extensions in the ground plane. Then we created, gave the same extension in the substrate also. After that, we created a copy of this patch antenna. So I will make a copy of this one again. I'm deleting it. Now select this patch antenna, copy, Control C and Control V. So the advantage of this Control C and Control V is that we are able to create a separate object that is not linked with previous object. So whatever changes we do here, that will not be impacted here. Okay. So let uh, let us make a duplicate by the relationship. With this, I'm creating a duplicate and I'm moving it in Y. T. So now if I change the dimension of this antenna, I am giving an extension of 10 dB in length. So you see both the antenna elements are changing. So both these antennas are not independent. I want an independent copy. Then what I can do, I can copy and paste. Now if I change the properties of this antenna, sorry. Now I give this uh, displacement of 50 mm. Then click here and change the dimension of this one antenna. So you are able to see that this antenna has an increased length, whereas this antenna has not, it has the same length. So by copy and paste, we can create isolated elements, isolated copies that can be controlled separately. And if you want to link them simultaneously, then you can do that also. So I am creating a separate copy of this, because the dimensions of the patch are same. So I don't want to make unnecessary engagements here. So both now this copy and paste. Now I have deleted the move operation. Now I'm giving it a rotation of 90 degree, so that we can simulate the polarization diversity. So with 90-degree rotation, we are able to see that this feeding edge, uh, this is rotated on the z axis. So it was already at 0, so it is still at 0. This edge is still at 0, but it has rotated like this. And from this point, this left half, it was having a length of wg by 2. So we have this wg by 2 placement here, and we also need to move this at this point. So first, I give this like a direction like this, and initially 0 0 0. So there is no placement. Now I am giving it in x axis. In x direction I am not giving, I am giving in y direction, wg by 2. So this has moved upward. Now I am giving it wg by 2 in x axis plus wex. So now that input, the feeding port, the edge of that feeding port is touching this substrate edge. Okay, same we did with the rectangle, this one. So we made a copy of this, say a separate copy, then apply a rotation of 90 degree. Then the movement, the displacement we gave wg by 2 plus wx plus wg by 2. Now this is completed, and then we selected, we have to make this one also. So go to right, and select this one, and you can select this fit this selected object here. Now we go to port 2, select the integration line, and we are going to define a new line here, and then click OK. Now if we click here, fit all, then select this region. So this region is also extending. If you go to top view, you can see in y-axis the region is touching the wave port, but in x-axis the region is extending. So we need to remove the padding in the x direction also. So in positive x direction, we give the padding to 0. Now click OK, close this, and so this is our antenna. Now we have two antennas. One is will be radiating in y direction, another one will be radiating in x direction. So both of these direction are orthogonal. So we are successfully able to place this orthogonal polarization. Let us verify this one. So now you can see our simulation is completed. Let us click here, check the S parameters, add S to 1. Okay, now we are getting minus 37 dB. And what happens if I remove this LX, WX, let us make it 40, and let us make it 35. Okay, let us try now. Okay, from P. Now go to S parameter, and now you are able to see that even our antennas are close by this much amount. The spacing between these antennas is very small, only this much gap, and still we are having an isolation that is better than 25 dB. And if we check from here, the spacing is at least 3 times that of the spacing we just had, and here we are having minus 12 dB. So all this is happening because one of the antenna is radiating in a separate polarization. This you can say that this one is a horizontal polarization, then this one is a vertical polarization, or it is radiating in Y. It is Y polarized, it is X polarized. So the polarization, due to polarization diversity, we are able to place our antenna elements close and still get better performance. So, but what we can do next, we can copy this design and paste it here. Now we can extend this up to a certain point. Like what else we can do? We can place one copy of this antenna here, one copy of this antenna here. So that will be like creating separate copies. So we might have 4 cross 4. So this was 2 cross 2. All these 4, this this is 2 cross 2. This one is 2 cross 2. This one is also 2 cross 2. Now we are going to try 4 cross 4. So in order to try for 4 cross 4, let us create another copy of this patch. I'm making it isolated. You can design on your own. And now I'm giving it a rotation of 180 degree, and then I will move it. So the movement will be in Y axis. I'm giving it L. How much did we apply there? Let us see LX and click OK. Let me give it WEX in Y. So in Y I am given at WEX. In L I am giving it, if I make it 0, then we see that this edge is touching at this point only. So now we need to shift to this point. So the total displacement is LG plus LX. LG plus LEX. Now click OK. So here we have placed this antenna. Again, we are making a copy of this patch, and now we are giving an operation and now we will be rotating 270 degree, and then from here to here we need to move. uh, so first give it a displacement. Now I am giving this minus wg by 2 comma 0. So this edge has come at this edge. Now we need to move it here. So now we will be giving it lg plus lx. Lg plus lx would be okay. Now we will lg by 2 plus lex. Let us try this one. If that is fine. Okay. So now we have, instead of lg, I should be having wg by. So now we have 4 ports, and what we can do, we can change this lex and wex. Wx is 35, we change this to 35 as well. Okay. So now our design is completed. Now we need to add more ports. So in the same way, we are going to apply the ports, make 2 copies. In rectangle 3, I will give the rotation of 180 degree. Then I will displace it, and the placement was this one. Copy this one and paste here. Okay. Again, in rectangle 4, first we need to apply the rotation. Rotation is 270 degree, and the movement will be same as this one. Okay. So now if we go to the isometric view, we can see this is patch port 1, second patch port 2, third patch port 3, fourth patch port 4. Now we need to set the excitation, and you can see this is the integration line for port 3, this is the integration line for port 4. So this is invalid. This direction is left. So I will go here and go to the back side. Now I select this antenna, fit it, and double click here, define this new line. Okay. So now again I need to go to isometric view and select all. Now I need to see this antenna. This one is in negative x. Negative x is over, I think left might be. Okay. So left. Now fit this selected point. Go to this port. Define then integration line. Click OK. And any query so far?
Participants are requested to please drop your queries. You may ask if you have any questions.
Okay, so the modeling part should be clear. If you have any query, you can ask. And if you are listening carefully, then at this point also we will be having some problem. So you can see in in y direction, this one is touching the waveport, this boundary is touching the waveport, but this one, two boundaries are not touching the waveport. So we set padding to 0. Now this radiation box is exact touching all the edges, uh, and only in Z direction we have a padding. So this padding is very critical when we are calculating the far field results. And again, this padding should be minimum lambda by 4, but I am using 20 as a random because I don't want to simulate for half an hour. So now the simulation, we can simulate this. Now if we check the results, now you will be able to see there are 16 S parameters. 1, 2, 3, 4, 5, 6. So from S11 to S44, there are 16 parameters that you need to analyze now. So we select these four and create a new report. And as soon as we will be getting the Swati, is it visible now? Vikram?
Hello.
Okay. So I hope now I am visible. I don't
Yes,
know
sir.
when
You
I
are visible.
got disconnected. So should I start with this from the simulation results? I think
Yes,
I
sir. You can
covered
start.
this. Okay. So we have designed these four antenna elements, and then we have given the radiation box. The padding in all four direction is 0, and these are the simulation results. So here we are able to see that we are getting isolation better than 25 dB at all four ports. Okay, but these are results are not reliable. Why so? Because first of all, let's check this setup. In a setup, we have set this number of passes to 6 only. We should set this to 15, and we should set this to 0.002. Before going for fabrication, these two this step should be taken care of. And one more thing, in the region, we can give this padding as a variable, and right now I am setting it to 0. So you can give this padding as variable, and you need to apply the parametric variation by increasing this length, and the minimum padding by 4. For the purpose of fast simulation, I am using 20 only. Otherwise, you should take consideration of this one, and with that, you will be getting accurate results. Now, once you make any changes here, then the results will be discarded. So you will have to again simulate, and it will take around 2 to 3 minutes here. And until this simulation runs, if you have any query, you can ask. This thing is visible. There will be a technical issue from so till the simulation is running, you can ask questions if you have any query.
Sir, one request is there from the participant to please explain how to make mirror and port
How to make mirror? Okay,
and ports.
mirror and ports. Okay, so mirror image is a let me go to new, new design. So we create a sheet here, and I will change the direction of this in Y. So you can see this sheet is placed around in X and Z plane, and the position of this sheet is Y equal to 0. Sorry. So you can consider this sheet as a mirror, and if there is a mirror and we are placing a object here, so the copy of this mirror will be displayed here, and it will have same depth as this one. Okay, so if you uh, this cylinder is placed in Y equal to 1. Okay, now Y equal to 1 is on that side. So when we are creating a copy of this, a mirror image of this, so this cylinder will be placed at -1. Okay, so let us click here and create a mirror image. uh, we can have two type of mirror. We can either move the object with mirror, or we can create a copy of that. So I am creating a movement, and in that movement I am starting from 0. So that point that I selected, that is known as reference point, and the second point I am selecting, it will create a vector alongside this. Okay, so now like this. So if I double click on this properties of this mirror, what you see, the base position is 0, 0, 0. So our mirror is placed at the origin, and this direction is showing that our mirror is placed in YZ plane, because the normal of that plane is Y. So we are in -1, that means Y, negative Y axis, or we can place it to positive Y axis. There is no issue there. Okay, so now we have created a copy. Okay, similarly we can do create a copy of this. Initially we created this platform, now we created a copy. Now the mirror is placed at this sheet, it is placed at 0, and that mirror is of infinite length. We have this just displayed the finiteness only. So I will go to here, select it opacity. So now this object has a mirror. This is the mirror copy of this object. Now what happens if we rotate this? If I rotate this by 10 degree, what will happen? If our mirror is rotated, then this copy will not exist here. This copy will be rotated. So that we can design in let us give it 0.2 in Y and -1 in and +1. Okay. So now the normal direction is not along the y-axis, that is slightly rotated. Okay, so now you can see, uh, let us remove this. Now from top view, you see this mirror is here. Okay, if I change this to 1, so it is a 45-degree mirror. So now this is also a mirror copy, but the mirror is placed here. Okay, along this line the mirror is placed. So we can control the position of mirror and its position. Okay. Now uh, let us set it to y-axis only. So the rotation of mirror is clear. We can set this mirror rotation, and now let us see the left view. both the elements are in same axis, right? And here both the elements are same axis. Here also their height is same. From here you can say they are placed at same height. Now what I am doing, I am creating an inclined mirror in Z direction. So you see that mirror was placed something like this. So that is why this copy is created like this. Okay. And from top view, what we can see, from top view, you can see that this copy is slightly rotated due to rotation in the mirror, and still it is directly here. Now, if I also give a variation in x-axis, then it will be like this. And go to the right part. Okay. So like this, you can control the mirror placement of the mirror. Sorry, the rotation of mirror. We have just changed the normal direction. Then the mirror is changing. Okay. Now, what happens if I create this mirror in x direction instead of y direction? Now, the normal of this mirror is x direction. That means my mirror is placed in yz plane. So if my mirror is placed in yz plane and my object is on the y-axis, what will happen? A copy is created, but it is remaining at the same point. Okay, it has not replaced. Now, again reset this. I'm creating a copy in y direction. Okay. So now from origin point, you can see we have 1, 2, 3, 4, 5 blocks away this point. This copy is also, this is our original object. Its copy is also 5 blocks away from this position. Now, if I set this to point 2, the base position in y-axis I have changed by point 2. Okay. So now the earlier the mirror was placed in xz plane at y equal to 0. Now the mirror is placed in xz plane, but y equal to zero point 0.2. That means our mirror is placed at this point. This sheet will act as a mirror. Okay. So in that case, we measure the position from 0. It is 1, 2, 3 blocks. Whereas from here, 1, 2, 3, 4, 5 blocks. So the mirror is here, and from this position you can measure 1, 2, 3, 4 blocks, 1, 2, 3, 4 blocks. So you can control your mirror by these positions. Now let us place this rotation. This is 11.11. This is 00. Okay. This is 11 and this is 00. So now I want to create a mirror at around this edge. So what I can do, I can give the normal direction to 110. Now this mirror is creating a copy here. Okay. Earlier, the previous operation is also cascaded here. So we can design our mirror. You need to imagine at which position the mirror will be placed and what will be the normal direction of that mirror. Okay, that you need to check. Any more queries? So let us discuss these results. Unable to start. Okay, it got some error. You will have to restart the simulation. Any more queries? Okay, so by the meantime, the simulation is running. I want to show you a paper in the workshop. This paper is a open access paper from IEEE. You can download this paper. It is open source, so anyone can download this paper. And I found this paper very good that it covers all the techniques that exist for MIMO antenna. So the problem with our design was when we are rotating this, so how much rotation we can give? We can make maximum four combinations like this. So we can have up to four cross four MIMO antenna, and all of them are having different polarization. So at the receiver side, the polarization should match in order to accept or accept the incoming signal. So there might be some variations. So what we can do, we want to have a fixed polarization. We are not giving polarization diversity. We want to place our antennas like this, not like this. This has opposite directions. We are not. We don't want it to be placed like this. We want to place our antennas like this, and we want to place our antennas like this and as close as possible. So for that, there are several techniques there, and you can find those techniques in this paper. So uh, uh, this problem is called mutual coupling. So both the antennas are placed nearby, so they will be coupling with each other. So they just like the inductors, when two inductors are there, then they are uh, exchanging field with each other, that is mutual inductance. So now we have a mutual coupling between our antenna elements. So several techniques are there. One is trans isolation in the transmission mode. So what we can do when one antenna is transmitting, the other antenna should not transmit like that. Then isolation in receiving mode, that is when one antenna is receiving, then other should not. So other method that are that we need to practically optimize, because the main objective of MIMO antenna is to have increased capacity. So capacity can be increased when all the antennas are working at the same time. So for that we have what we can do, we can have a decoupling network. A decoupling network, we need create some uh, either we can create some discrete elements like inductor capacitors, or we can design some quasi elements through the microstrip techniques, and that will act as a resonator at those frequencies, so that the signals are not transmitting from one another. Then what we can have parasitic elements. So these parasitic elements are isolated elements. They are smaller in size or larger in size. So those can also decrease your isolation. Uh, those can also improve your isolation. Then we might have defected ground structures. On the ground, we can cut some portion that will somewhat reduce the isolation, the coupling. Then we can have a neutralization line. Neutralization line is neutralization line is I will copy this, and for example, in this diagram, sorry, in this design, if I create a transmission line that is connecting these two antennas, okay, what will happen if we are creating a transmission line? Okay, um, now if you connect these two antennas, What would happen if we have a transmission line made up of copper and we are connecting the feeding ports of both the antenna elements? Any guess, Swati?
Yes, sir.
What will happen if we connect a transmission line connecting both these feeding ports? Whatever signal we are transmitting here, it will be
Sir,
bifurcated
no
here.
idea.
जो पोर्ट 1 से आप
Yes,
सिग्नल दोगे वो यहाँ पे दो पार्ट्स में डिवाइड हो जाएगा. देन half of the part
correct.
will come at this point and will
Mm-hmm.
again here it will be divided into two parts. One part will be sent to antenna and other part will be sent to your source. So this
Source,
method,
correct.
so in this method what we are actually doing, we are actually decreasing the isolation. We are uh, directly connecting both the ports. Okay.
Mm.
So how it will, how we can use this kind of transmission line and still decrease the iso, still improve the isolation. So what we can do, if that the part that we were trying to cover here, and when, earlier we just seen like here what we can see from electric field lines. This if we see here and select so what we can observe here, from this edge of the antenna, some part of the field is connecting with this edge, that is coupling. Now that part will traverse back, that will traverse back to this feed line. That is your original mutual coupling. So I want to reduce that, but in order to reduce that, what I am doing actually, I am doing connecting a extra line that is directly connecting the field. Now, how we can control this division of the signal? If you have studied about the power transmission lines, power divider, how we can control this division? We can change the impedance, characteristic impedance of both these transmission lines. Okay. So if our original feed line is of 50 ohm and we give it this transmission line an impedance of 100 or 120 ohm, what will happen? It will only select a very small part, right? It will only sample a small part. Let's say that 90% of power is transmitted from this antenna, transmitted to this antenna, and 10% power is divided and sent back to this line. Okay. Now, in the coupling, 10% power was coupled to this port, and that 10% power was connecting here. So now we have this length, uh, one in this port at this position. Let me show you. This is my original antenna, and this is my second antenna. Okay. Now this is the feed line that is exciting, and some fields are some field is radiating from this antenna and it reaching this point. Now I have this antenna also connected to a feed. So from this position, that field is transmitting in here and like this. Okay. So one of this user was here This is port A and this is port B. So from A, I am giving a signal. That signal is radiated by the antenna, and that radiated signal is being coupled by this antenna. And from this feed line, it is reaching to point B. We don't want that. So what we are doing, we are creating a direct connection between these two. There is a direct connection. Now, the signal that, let us assume the signal that was coupled, it is of 10%. So if I add another 10% from here, the resultant here will be 20%. Now, if I can control the phase of this signal, if I can control the phase of this signal, and I can control like this 10% was coming at 45-degree angle at this point, and this 10% is coming at 225-degree. So both of them are out of phase, so they will cancel out each other, right? So in that way, we can utilize this neutralization line and we can implement an isolation. Okay. So now we have just created a straight line. That is why it is not visible for you. But what we can do, instead of a straight line like this, we can create a structure like this. Any random structure and connect that line here. This is possible. So by using this main ring technique, what we can do, we can reduce the coupling. So in that we have to make sure that this neutralize this line, that is, it is called neutralization line. This neutralization line is sampling only the sample. If our S21 was minus 10 dB, that means 10% power was coupled. So this neutralization line should only take 10% power from here and it reaches here. Okay. So what are the disadvantages of this technique? In this technique, we are extracting a signal that should have been transmitted. Okay. So basically, we are reducing the efficiency. The second limitation of this is a transmission line. So we want an exact 180-degree phase shift, right? So for a fixed transmission line length, the 180-degree phase shift will be only for a particular frequency point. Otherwise, it will be different. At some point, it will be 170. At some point, it will be 190-degree. So then, this kind of transmission, this kind of method gives isolation improvement at a particular frequency or in a very narrow band. Okay. Now, let us see the results. Okay, still there are no results. I think there might be some error. So these were the original results. So again, I am reminding you that these results are not reliable because we have set these limitations. Okay, and I hope you got to understand this also, and this transmission line mechanism. And this paper has more discussion on different sections, and it has given a very good comparison with these. And finally, there is a you can see that this is a antenna that we are placing in the same configuration. Then there is an isolator. It works as a parasitic element. It reduces the coupling, and you can see from here, without the isolator, the field was coupling more. With the isolator, the field coupling reduces. Okay. And there are some more methods based on metamaterial or high impedance surfaces. You can explore all these techniques, and this table, you can see these conclude the different techniques. What are their benefits? What are their drawbacks? So based on your own requirement, you can select a particular technique and implement that. Okay. So I think I took more time than expected, and besides that, in MIMO antenna, there are certain parameters that we need to calculate. So I will calculate those parameter for this antenna. So the first one is ECC. ECC is a con correlation between the transmitted sig signals. The formula for that is this. So we copy this, and in HFSS, in the results, right click here, sorry, in the results, select a graph. Now we are not going to select this one. We are going to select this output variables. Okay. In output variable, give this name as ECC and paste that argument. Okay. So right now it is giving an error. So uh, let us see what is there. We need to select the S11, its conjugate magnitude. Okay. So select S11 conjugate and like this. Now I need to make the magnitude of this. So okay. Then we are first we add this one. Then we need to multiply it by S12, S12, and here we will be selecting the magnitude. Okay, and click here, click star, insert into magnitude. So now we have conjugate of S211, then magnitude of S12, both multiplication plus. Now we have the same but reverse. So copy this one and click here. Now we place conjugate of S21 and magnitude of S22 like this. Now we have to enclose this and make it power. Okay. Like this. Plus it will give you an error if there are some mistakes in the formula. Okay, instead of plus, we need to divide this one, and we will be selecting this 1 minus magnitude of S11 square minus magnitude of S21 square. Okay, 1 minus S11 magnitude, insert into the expression S11 magnitude power 2 minus magnitude of S21, insert into expression, again make power 2 . Okay, so then multiply. Now again same thing is there with different parameters. Copy, paste. Now here we will be having S22, S12 and S22. Okay. Then we add this variable. So now click done, and now you can see from variable and output variable. Just above the S parameter, we have a output variable. We can plot this ECC, its magnitude, and click new report. So now you see our antenna has this kind of ECC. At around this point, we are getting a peak, and that peak value is 0.02. So ideally, we should be having it less than 0.05, I think. Okay. So this, I will give you this document. So similarly, we can also define the diversity gain. We can also define the track, and then for the mean effective gain, there is no direct calculation in HFSS. You have to select the overlays and go through all these steps. But what I do, I prefer to design the antenna in HFSS because that is more comfortable for me, the design and simulation. Then once I have finalized the design, I have finalized the uh, other parameters like isolations and return loss. Then I export the design in HFSS from HFSS to CST, and CST has a direct for calculation of these values. It can CST in CST we can directly calculate ECC, we can directly calculate DN, we can directly calculate MEG and other parameters. So if you have access to both, then you can apply this. Otherwise, you can use the help of this document and create your own variables to calculate ECC, diversity gain, and this mean effective gain. Okay. So I will be sharing with the organizing team this document, so they will give it to you. Okay. And if you have any queries, okay. So loop is forming. Mr. Ramesh, in what reference you are saying loop is forming?
Sir, actually, you asked that question, no? Two elements connected with a transmission line. For that, the
Yes, yes.
answer is there from participant.
Okay. So that I have sent you that this is creating a loop, but at this junction, what we want to do, this signal that we are receiving, it is out of phase with this signal. Okay, and their amount is also same. So that requires very parametric user optimization. Okay. So you can control the width of this transmission line and control the impedance. If higher the impedance, lower part of the signal will be sampled. Okay, and you can give main ring here so that it gets you the desired outcome and it gets you the out of phase ratio. And do we need to unit the transmission line? Afrin, can you explain this question? What do you want to know about this? So I will stop the sharing the screen so you don't see any infinite loops. Okay. So Afrin, I did not get actually your question. Can you please elaborate what you want trying to ask? Okay, so any other participants have any query?
Sir, Afrin has clarified the question.
Okay. Sir, I am asking regarding designing, do we need to unite the neutralization line to the feed line in the design? Yes, you will have to unite them. and it should be of the same material. Normally we use copper. Otherwise, if you are designing with some other materials, then the material should be same. Or file in MIMO antenna design 4+4. Okay, so I will try to get it. And Swati, can we have the transcript in the recording?
Yes, sir. Transfer we will provide to all the participants.
Okay, so in the from that we can create the transcript. Otherwise, I will have to write every step. Okay.
Sir, I'll provide the transcript for to the participants and
Okay.
upload on their canvas.
Okay. Okay. So from transcript you can have, and Swati, please send me the transcript also. So I will create use AI tools and create a systematic step-by-step guides. Okay.
Okay, sir. I'll do that. Participants, if you have any query, you can please drop in the chat box or raise your hand. Sir, I think now there are no more queries for today's session.
Okay. So thank you everyone for patiently listening, and I hope the session was helpful for you. So we will meet tomorrow again. Thank you very much. Okay. Thank you, Swati.
Thank you very
Thank you,
much, sir.
Vikram.
Thank you, sir.
Dear participants, next session will be tomorrow from 9 a.m. You are requested to kindly join by 8:45. Thank you.